So this was a collaborative project with universities in Taiwan, and they sent several students to CMU for 1 year. And so many of, on top you see the students who, some of them are CMU students, but many of them came to visit. And on the bottom you have the faculty list. Max Kron was a postdoc for some time at CMU, and he also contributed as well. Taiwanese faculty, etc. All right, so because I'm going to go through a lot of things, I figured let me start and mention the main points that I want to convey. And they are that physical encounters offer a really powerful way for people to understand which people they're trusting. So for example, if you send an email to someone, or so you receive an email from someone and says, okay, this is the person you've met October 14th during this talk, you get a lot of context because it's a physical experience. And that's one point that we make use of in this work. I'm also going to present a completely new class of security protocols that actually include personal people mobility as part of the security protocol. So in order to defend against the group in the middle attack, which I'm going to present, and Sybil attacks, we make use of the physical mobility of the person. So that's, I think, quite unique. That's one of the unique aspects of the work I'm going to present. So just remember these two things. So essentially the problem I'm going to talk about is key distribution in groups. So you have a group of people, they want to later on securely communicate, either email or set up a file system or send secure SMS. How can you exchange keys in a secure fashion? And it's not as simple, you may think, well, establishing keys is easy. So let me go through a little bit, and then you're going to see a lot of the challenges that come up in this context. So the specific problem statement is that we want to get everyone else's public key. So because public keys can later be used to set up any shared keys, right? If you have everyone else's public key, it's easy to set up, and a lot of work has been done how to set up shared secrets based on public keys. And so you can use encryption, you can use non-repudiation to attribute messages, as well as, of course, set up shared keys in subgroups. And so notice that establishing the authentic public key is a lot harder than establishing a shared secret. And I have another slide on this, why this is the case. You can already think why this is true, but it's really a lot harder to exchange authentic public keys than establishing a shared secret. All right, so the attacker model is that there may be a malicious person in the room, and that may be able to overhear or see information, right? So there was one scheme where people wrote the password on a board, and then everybody typed in a password, and the system established a shared secret based on that password. That's obviously not secure with an attacker who is physically present. And also, all this, the context in which I'm going to describe this is in a setting where people have mobile phones and they use wireless communication to exchange keys. And obviously wireless messages are not secure. Anyone can easily eavesdrop or intercept or inject messages. We also say that even a valid member of the group could be malicious, and that member may perform a Sybil attack and try to inject multiple identities or remove valid members from the group. So those are both attacks, or do both at the same time. Essentially remove a person but then inject a different public key for that person. Now we're going to make use of an out-of-band channel, and the in-band channel will be the wireless communication, which people cannot see, right? There are a lot of attacks, wireless-based attacks. And the issue is that this in-band channel is invisible, right? You could communicate with someone here, Minoxi and I, we could say, okay, let's establish a key. You know, we can see the protocol is doing something, but instead what's happening is my phone communicates with someone upstairs, and that someone upstairs communicates with her phone. And now we think we're communicating, but actually communication is going, you know, through this malicious person on the second floor. And that's a big problem because people cannot see a wireless communication. So what we really want is to have a human verifiable channel, an out-of-band channel like a cable where also near-field communication can provide some good properties to say, well, these two devices are really nearby, or a human visual channel with action. And there's been a lot of out-of-band channels that have been proposed. The one I'm going to make use of is called Seeing is Believing, which is one that we've proposed several years ago, which uses the ability to take photographs with a camera. So the idea is that one phone, in this case, so we're going to have 6 phones, and the color determines the name. So we have Pearl and Amber that want to exchange a key. So in this case, Pearl displays a 2D barcode that encodes the hash of the public key. And now the other phone, Amber, can take a picture of this public key and detect the 2D barcode and extract the hash, etc. And then you can send the actual public key via wireless communication. So this is a really useful mechanism because as a human user you can see what's happening. Look how difficult this would be to intercept. The attacker would have to get in between the two phones in a way that's invisible to the two users, which is pretty hard to do. Right? So we believe this is a useful channel. Now, only using out-of-band channels would be very cumbersome for large groups. So if you have a pairwise secure exchange, which the Seeing is Believing provides, you would have to perform a lot of pairwise interchanges for large groups. Right? Like for people in this room, there would be roughly 40 people here. So it's roughly 40 squared divided by 2, roughly maybe 800, around 800 mutual exchanges would have to happen, which is a large number. That obviously does not scale to large groups to do this pairwise exchange between any pair of people. So we're going to present protocols that can exchange authentic information in a more secure fashion than, or in a more scalable fashion, I should say, than this two-way exchange. All right, so prior solutions include the PGP key signing parties and public key infrastructures. I was not going to go too much into detail because they're actually, PGP key signing parties were not that easy to use. They had a lot of vulnerabilities as well. And I'll be happy to talk about this more if people are interested in. But simply by the fact that 20 years after, 20 years after PGP was introduced, probably even more, not everyone is using it. And so that indicates there's some usability issues that we're trying to address here. Also with PGP, public infrastructures, there are a lot of issues. As we know, also research done here identifies the insecurities of SSL and TLS. Is Chris Zagoyan here? I think he's a student here, not anymore. But
well, he's still a student.
He's not here, right? So he did some useful work also demonstrating this. There are a lot of issues with PKIs that we want to resolve. And again, the main point, I come back to my second slide. With these approaches, you don't really know who really is the individual who's now sending you that email. And we want to truly tie it back to the physical person who sends that email message. And I think it provides a big advantage over these previous mechanisms. So one problem in designing these protocols is that people actually can't count large numbers of groups. There's an anecdote where I think nine computer science professors went to a restaurant, and the waitress asked, "How many people are you?" The first person says, "We're 8." The next person says, "No, we're 10." Then another person says, "No, we're 11." So nobody got it right. They're all CS professors. I wasn't there. I just heard the story. But we actually did some studies as well. So this graph indicates how many people are actually present and what the number of people were that people counted. So you see for 8 people, already one person or at least one person made a mistake. So we saw quite consistently there are not a lot of data points on this graph. We did more user studies than this. But as soon as there were more than 8 people, somebody in the group started miscounting. This is a problem that people can't count in large groups. And so there's also, of course, prior work in secret key establishment, that's why many people think this is an easy problem as well. But the authentic key is harder to establish than the shared secret, because it allows you to, it's strictly more general approach, right? If you exchange a authentic public key, you can easily deduce a shared secret, right? There are a lot of protocols to accomplish this. But vice versa, it's insufficient. Because let's say we all share a key, and we then say compute a message authentication code on our public keys and send those out, you cannot authenticate where they're really coming from, because everybody in the group has the same shared secret. Right? So still, Apu could send a fake key for me because he has the group shared group secret, and all of you may store it because he may also be able to, sorry to use you as an attacker, he may also be able to block my message, and then all of you get the wrong key. So this is a strictly, exchanging public keys is actually much harder because it's strictly more general solution. One way in which we broke a lot of the previous protocols, pretty much actually all the previous protocols in this space, is called the group in the middle attack. The way this works is that we have 4 members. I'm not sure if the colors come out that well. So one is supposed to be orange, blue. There's a black person or a red person. So anyway, so we have a group of 4 people, but there's one person who's malicious. I believe it's this person here is malicious. That person creates fake identities and creates 2 different subgroups. So to these 2 users here, this malicious user creates an additional malicious identity, and then these 2 people think, well, I'm in a group of 4 people. Similarly, to this legitimate person, this malicious person creates 2 other different identities. And now, from the perspective of everyone, they're in a group of 4 people. But in this group, there's 1 fake user, and in that group, there are 2 fake users. But look, when people just look at their cell phones, that's what they see. They see, I'm in a group of 4 people. But virtually what's going on is this attack is happening because people cannot see the wireless communications. Based on this attack, we're actually able to break all the previous protocols, like the one where people write the password on the board. Right? You can very easily then run this attack. So we essentially want to create these protocols where we have a secure exchange of authentic information where every individual can only contribute a single public piece of information. And you're going to get authenticity for that piece of information. And essentially map each digital piece of information to every physical person. We also want to be tolerant to operator error because people may run these, or non-experts may run these protocols, or most likely non-experts will run these protocols. And we don't want to have people count in large groups. We don't want to have people having to compare data in large groups, right? So one solution to make sure that there's no man-in-the-middle attack is to compare the public information you've received. It's like to display a hash value and then go around to everyone, make sure everyone has the same hash value. But that's also pretty cumbersome. We want to avoid this as much as possible. And then, of course, also be tolerant against the local attacker. All right, so does somebody have a question at this point? So this is the...
I have one question. On the previous slide where you were talking about the malicious party, so the malicious party is like an authorized entity within the group. Is he supposed to be there, but the other members just don't know that?
Right, there are 2 cases. There are 2 cases. The attacker could be standing on the side and just observe the space and trying to inject his or her key into the group.
Okay.
In another case, in this specific case, the attacker is actually a group member.
Oh, okay, okay.
Which is obviously the much stronger attack.
Okay.
And in this group in the middle attack, the attacker does need to be able to have the password, for example.
Okay.
All right, so I'm first going to present the gangs protocol, which was our first attempt in this space. And essentially the goal was to have scalable, authentic local data exchange. So in a room with people, in a room of people, we could all exchange information very quickly and obtain everyone's as public key. Again, ensuring that every person can only contribute a single public key. So if somebody injects 2 keys, we want to detect this. But again, we cannot count. So the question is, how can we accomplish this? And that's what the protocol tries to achieve. I'm going to show examples with 6 phones, Pearl, Amber, Indigo, Red, Violet, and Jade. I think you can now see the colors a little bit better. The goal is to only have order of log n interactions, right? Not requiring n square number of interactions, only require limited counting, and only performing a limited number of group comparisons. And the key idea we used in this protocol is that people have to physically move around. And if somebody attacks, that attacker will likely having to split up into 2 people and move to different groups at the same time, for example. Right? Because a person can't easily divide themselves into 2 physical entities. The protocol should be secure. But there are some caveats as I'm going to present. But I believe this is one of the first protocol that requires physical mobility as part of the security protocol. So the way we're going to do this is, in the first step, we're going to collect everyone's public information. And then we redistribute it, and then we want to identify and map that information was learned back to the physical user. All right, so first we're going to collect. And in this phase, we already want to exclude members who should not be part of the group. Right? There's one person standing on the side. We all know this person should not be part of the group. So this first phase should already exclude that person. So we have one leader here, and a Violet in this case becomes the leader or the root. That's actually already one disadvantage of the protocol. So this is actually an active area of research we're still working on to make these protocols much better. And so this was our first attempt. And you can see there's still a lot of ways to improve it. So first of all, you don't necessarily want to pick a leader. One time we ran the protocol, 2 people absolutely wanted to be the leader. And they absolutely did not want to give up not being the leader. So I said, come on, be reasonable. There are only 10 people. And they just absolutely didn't want to give up. They said, no, I want to be the leader.
Could you run this like a zero knowledge group, like a model? Could you run the protocol multiple times to see?
Right. The difficulty is you start with nothing essentially, right? There's no authenticated information, there's no crypto information yet. And so you're going to see in a later stage, we do split up the group into random subsets that are not controllable by anyone. But at this stage, they share nothing. Associating the right phones with each other is actually pretty challenging. Can go into some of the technical challenges as well. Actually, many of the design decisions were also made because we implemented this based on Bluetooth. And it's not easy to just broadcast something in Bluetooth. You have to get everyone's Bluetooth MAC address. And the way we solved this, actually, this encodes the public key and the Bluetooth address in this 2D barcode. And that was one of the ways we got around device discovery. So a lot of the things you're going to see, they may look awkward, but they were specifically selected in order to make the protocol implementable on these Nokia phones. Now we're building a tree of phones. And so in this case, Amber joined the tree first, and herself and Violet exchanged information. So now they both display 2D barcodes, and now 2 other phones can perform the exchange. And essentially, in this step, there's strong authentication that happens between the 2 phones, right? And so you keep building this tree, and now you can already see why it's a logarithmic, because you're building a tree. Any member could now perform this protocol with anyone who's currently present here. Right. So now at this stage, we prevented the external person to be able to participate in the group. So this is already accomplished. Now all these phones send the information up to the root, and the root redistributes it. Now the problem is that for this phone here, I think it's shown in the following slide, this phone only authenticated, I think this is red, only authenticated Jade. And all the other phones, information it just received. So you cannot trust any of those other pieces. So in the next phase, we now need to map the virtual identities to the physical identities of the people. And the way we do this is with the second protocol. That's going to be, that's called Gang's ring. And this indicates the green phones show which phones can be validated, and the red phones show which ones cannot be validated. So you see this is different for everybody in this group based on whom they perform the exchange with. So now the goal of the next phase is, again, for every member here to associate a physical person with all the red phones that they have. But that this wouldn't scale by itself. So we're going to leverage the fact that we assume that most people in the groups are legitimate. We assume there are not that many attackers who are present. And so we're going to trust other people that are part of the group to verify some of these other phones. And so we split the whole group up into subgroups, and then the subgroups have to meet. And the way this is accomplished is through a pseudorandom function that is non-predictable. So no malicious member could predict what the subgroups are going to be. So we're using this. There's a lot of cryptographic operations that go on behind the scenes here. Commitments are being exchanged, so you cannot predict the subgroups, etc. But the main point is that we're going to have two subgroups of 3 people each, and the members have to find each other. So now you should say, aha, this is not going to work that well in practice. That's actually true. Finding in a large room, finding all the people who are part of your subgroup can be pretty tricky. That's one other reason why this protocol actually is relatively slow. Because it's just, people have to move around. But now this is where the people mobility comes into place. And now once they're part of the subgroup, we do a separate protocol within the subgroup where, again, there's some seeing is believing exchanges, but now only unidirectional exchanges. You could say, aha, people are going to get confused. And that's true. People will be confused that they only have to do 1 in this stage, but 2 in the previous stage. That's another disadvantage here. But in any case, they all then digitally sign information and verify that everybody is truly present. And they actually have to perform also counting in the local subgroup. So everybody needs to say, yes, we really have 3 people. And then there's some additional signature operations that are being passed around. And then they compare a visual hash image to, this is a visual hash to make sure everybody truly has the same information. So you see the protocol is pretty involved, but this is, I do believe it's scalable, but it has the caveats I just mentioned, that people actually could get confused as well. There are a lot of different steps that need to be performed. Now, a good way to understand the protocol is for me to explain what attacks are feasible and to show how the attacks are being prevented. So I'm going to show 3 different attacks. One is one member tries to add an outsider to the group, removing a valid member from the group, or adding multiple identities to the group. And so the first one is the addition of the outsider. So red, in this case, tried to add black, his friend, into the group. But now once black shows up in the subgroup, the other members can say, okay, I only see 3 legitimate members and not 4. And like this, you can see an inconsistency that these 2 members need to know that this member should not be part of the group. And that's why these 2 phones are going to send an error code. Actually, every phone has to, at the end, release a decommitment, cryptographic decommitment that is necessary for the successful completion of the protocol. And if they say, if the phone detects an inconsistency, then they're going to abort and the whole group agreement, the whole key exchange fails. And so in this case, this member called black will not be part of the group. So the phone thinks there should be 4 legitimate people, but these 2 members say there are only 3 legitimate people present. That's where the inconsistency is detected. Now, if a member is being deleted, so in this case, red again is malicious and tries to, I believe that's jade. No, this is indigo. Oh. Who is this? Gray. Forget what this phone's name is. Anyway, so there would be 5 members here and only a 2-member group with the phone that's being attacked. Then that phone will also say, I'm part of subgroup 1. And that member is also going to show up. Oh, sorry. I think I skipped something. Right. So that member is also going to show up as well. And it could be that red should be part of that subgroup and then doesn't show up. Actually, there's a slight mistake here because already there will be 1 too many members in subgroup 1. But in addition, what happens is, what's explained here is the actual phone, the public key will not be known by the other members. Right? And the phone shows up and starts signing messages with that public key, and that's how this intrusion is detected. Right? The phones all exchange public keys, and as they all exchange public keys, and during this Gang's ring protocol, they all verify that all the other public keys are present. And when somebody starts signing with a bogus public key, that's obviously immediately detected. Now, what's... Mm-hmm.
Are the people also trying to kind of establish the identities? Like, will I kind of make a note like, okay, this is Adrian's key and this is Meenakshi's key? Or
right,
is it just...
that's an excellent question, because if we run this protocol here in this space, at the end you have 40 members with 40 keys. So you actually, in our UI, you have to go through each member and say whether or not you want to import them. So you need to look around and say, yeah, this is really, well, she's here, I'm here, other people are here, and then you would accept the keys. And people whom you wouldn't know, you wouldn't accept their keys, right? And that's a really good point. That's one of the difficulties in these type of protocols.
I guess you could take a picture of the person holding the phone next to them so you get both pieces of information at the same time.
Right, unfortunately it's not scalable. Right. But we've actually thought a lot about different protocols, but unfortunately this is a really hard problem to solve. So, but I think it's an important problem, which is why I'm giving this talk here. So I'm going to come back later to some of these higher level points, but ideally the protocol would just tell you, yes, this is the person you've met here, and you wouldn't have to do too much manually, but then somebody else could inject additional bogus information. You could say this is Virgil Gligor's key, for example, and I could inject that key, and now at the end everybody has Virgil Gligor's key, but he's obviously not here. Right? And then that's an issue.
Is it possible in this particular scenario for someone to capture a key by an authorized member of the group and then try to impersonate them and possibly change their key?
Right. Because it's all public key based,
yeah.
Even if you have their key, you can impersonate them. That's what this relies on.
But I'm saying, can they then, I guess if they were to send a message and try to say update this key, that requires the private key of the person. So,
exactly.
Okay.
Or even in this ring protocol I described, there are a lot of signatures involved, digital signatures, where everybody has to sign digital information with their private key, and then all the other members verify those signatures.
One more disturbance.
That's okay.
I just realized that, is there like a protocol if you use the Pico projectors? Mm-hmm. So my thought is that all these guys are getting...
Backup slides.
Oh, okay. I feel like everybody could just project their keys and then each one takes one picture and then maybe you're done. I don't know.
We have a protocol called Gang's projector. You send your key to a projector and then you check, make sure your key is correct. But then at the end, you still have to do the subgroup verification to make sure people are there.
I see, okay.
And to do that mapping, because otherwise somebody could project multiple keys again.
Right, yeah.
Right. But that's slide 70 or so. Anyways, so the third attack I'm going to present is where one attacker is performing a Sybil attack, and here red is, so this is the actual topology, and red presents another phone, the one with the mustache. So now the way this is being detected is because the attacker can't be at two different places at the same time. So in this case, the evil twin and the member are both in subgroup 1, but there's no physical person with this phone. And so these two members will say, well, I only see 3 legitimate members, but there should be 4 members, and that's how it's detected in that case. And in another case, the 2 end up in 2 different subgroups. And so in this case up here, red wanders from one group to another, first performs the exchange in one group, then performs the exchange in the other group. This should be detected by people. So in this protocol, unfortunately, all the members have to be quite vigilant to catch these kind of cases, which most people are not. So this protocol can work well with computer scientists, but if you truly want non-experts to use this, we need to make this a lot more robust. Well, anyways, but that's where the inability to split yourself up into 2 people comes in, where the physical mobility is important. Then you can see why the protocol resists these kind of attacks. Now, another case I haven't mentioned, you may get unlucky, and all the attackers may end up in their own subgroup. Right? So if the attacker claims, say, 3 malicious entities, and then all those 3 entities end up in their own subgroup, then obviously nobody will complain. And that's yet another disadvantage. So we've done the analysis. So actually the detection of these attacks is probabilistic. And you're relying that the legitimate member ends up in the groups where the attacker is, and then detects if any anomalies occur.
So, sorry, could you repeat how subgroups are selected? How do you decide who goes in what subgroup?
Right. So specifically, we collect everyone's public keys, but with the public key, you also have a commitment. So you commit. Actually, it's a small one-way hash chain. So you compute the hash chain with, say, I think we need 4 elements. So you just add 1 to your public key, and after all the information has been collected, everyone discloses 1 pre-image. And then all the pre-images are necessary to then, that information is hashed, and based on those hashes, you then split people up into subgroups. You can just sort all the hashes of everyone's information. And so the attacker cannot predict which subgroups are going to be formed, and cannot change, because that's very important. Otherwise, the protocol would just break easily. So it turns out that when you do the math, that the x-axis here shows the number of group members, and the y-axis shows the probability that an outsider is detected. And so you can see that the larger the subgroups are, the easier the detection is, but then also the exchange gets slower, the larger subgroups. So there are a lot of trade-offs we had to navigate. Now, in the implementation, we did this on the Nokia N70 phones. They're pretty dated these days. So we're currently working on a version for Android and iPhones that you hopefully can download in a month to actually do this. And I'm going to tell you why you'd want this too. So, GANGS, unfortunately, is pretty slow. So the GANGS tree, sometimes the taking pictures is pretty finicky. And so it can take a long time in some cases. You see here Indigo and Pearl, I think it is, or oh no, Pearl is on top. Anyways, the second and the third took a long time on this one exchange. Also the fourth and the fifth took a lot of time on that last exchange. on the SIB exchange. The dark bar shows one direction, the lighter bar the other. So they spend this much time to take the picture here, and then that much time to take the picture here. So you see, sometimes it can take several seconds. It took almost 12 seconds to take this picture in this direction. And of course, if you're outside also, this is not very practical because you have glare and the picture cannot be easily taken. So these are all disadvantages. Now then the gang's ring. So it took about a minute, 50 seconds in this case to form the tree with only 6 people, so it's pretty slow. But it also took 45 seconds then for the 2 subgroups. And it also takes time for the members to find each other. So the whole party took about 2 minutes for 6 people, and that's pretty slow. However, the reason I'm still presenting this is because I believe this is a really interesting research direction that people can work on, and it's a wide open space with a lot of opportunities for doing more work. Now the follow-up work we did is we observed that the majority of groups will be small. Right? Usually you only have 2 or 3 people, and the vast majority of time there are fewer than 9 members. And we noticed that with only 9 members, you actually don't need to use such a fancy protocol like we just had. You can get away with a much simpler protocol. So here now this protocol is called state, and again we do this data selection, and now people actually count, and at the end there's a simple comparison step. And let me briefly run through this. So everybody has to count how many members are present, and then also what information you want to share. Then you collect everyone's information, so they're actually Bluetooth broadcast. And then there's a verification step, and at the end the phones check that everybody clicked OK. But essentially, let's see, something I want to mention. Right, because we're using Bluetooth broadcast, the actual protocol we implement is slightly different from this. We had one leader who took a picture of everyone else. So all the phones displayed 2D barcodes. So it's slightly different that I'm going to go through here. But that's just for practicality of implementation reasons. So initially, everybody picks what data they do want to share. So people have phone numbers, they have websites, Facebook pages, public keys. They select what information they want to share and how many people are present. And then the phone broadcasts its information and collects everyone else's information. So we have actually one Wi-Fi protocol, and then you don't have to get everyone's Bluetooth address. But not all the phones are able to do Wi-Fi, so then actually the implementation we actually did was based on Bluetooth. And at the end you compare and make sure everyone has the same information. And one way to compare is just to simply display the hexadecimal digits of the hash. And just comparing a few of those digits can give you a nice level of security. At the end then you want users to click OK, say the comparison was correct. Now you may say, well, most people are not going to check anymore, right? You do these, like as security people we often make the mistake to say, okay, people check or there's always an attack or something. But the vast majority of time there's no attack, right? And so let's say you do this protocol 10 times. You're not really going to go and compare anymore and check, is there an attack? Let me make sure all the hashes are the same, right? There's usually no attack, and so people would just click OK. What we've done against this is we now actually display several pieces of information, and you have to compare which one is the same with the other people. Because words are the easiest to compare, we use word lists that then each phone displays a different list and only one of the 3 lists match. Now, when you implement these protocols, there are always so many side conditions that come up, and so you don't want that by chance two of the other lists match, right? Two of the random lists. You have to make sure that you guarantee that there's only one single match among everyone who's in the correct group. So this has been a lot of fun to implement these kind of protocols because there are a lot of corner cases that come up. But anyways, at the end, if everyone truly clicks OK, then the protocol succeeds and people can then accept everyone's information. So you see the spade protocol, maybe I should go back, is much, much simpler than GANs, right? So all you do is, let me explain the Wi-Fi case, because that's the one I had here. You just come, you say, okay, I'm in a group of 6 people, here's the data I want to share. You just wait until the phone collected 5 other people's information, and then you just do the verification step, and you click OK, and you're done. So it's very fast. It's not very robust, though, if there are different groups who do this at the same time. Right? If there's another group next to us using the same protocol, they're going to cross-pollinate. How can the phones here know that the key is from the local members and not from the members over there? So our Bluetooth protocol is more robust to this, where all the N-1 members display a 2D barcode of their Bluetooth address, and one member just goes around and takes all the pictures. So that was actually very fast to do. And at the end, you just click OK. So it's really easy, really simple to use, but it doesn't scale. Like in a group of this size, we could not have run this protocol. Now, we've implemented this and did some user studies, which I'm going to show. And we actually, in this particular prototype, we used flags to compare images. So we have 8 color blocks, and each color block has 8 different chances. So you get 24 bits for comparison. So you just compare that these flags are the same. And then you need to make sure everybody really clicks OK. Now the performance of spade was dramatically faster, which you can see here when you compare spade with gangs. Right? So the green bar, so the x-axis shows groups of different sizes, and you see gangs is just much slower and has a lot of variability as well, depending on how quickly the picture taking is going. Now we come to the another interesting case, which is, now what do we do once we have these keys? And we've implemented a Thunderbird plugin for secure email. So the scenario is that you collect keys, and then you go home, your keys get uploaded into your email client, and from then on, all your communication can be secured. And we've also implemented a secure intuitive file sharing that I'm going to present. And here it's, well, I'm going to go through this, and also secure text messaging, which I'll also present.
So in the context of secure email, these people must have been in a group to actually do this exchange, right? And then on they can go home and continue to exchange emails securely with each other, right?
Right, that's exactly right. So of course, you don't always meet people physically. So you want to augment this system with another system that can use other ways for learning other people's public keys. But in general, I believe that this can form the basis for truly secure key establishment. Because once you have the physical exchange, you truly know it's that person's key I now have. And then you can start using links from then on.
You can do PGP style then on.
But right, exactly. But you don't want to go too far. I actually believe that you can go at most 1 hop, because if you go 2 hops already, you don't know one person in the chain.
So you're relying on whatever authentication mechanism the phone has, just in case someone loses the phone, and then you have access. Whoever gets the phone has access to whatever public keys are already there.
Or private keys, especially.
Yeah, private key of the owner.
So what's actually interesting is in gangs, the private key was necessary in the protocol to do the exchange.
It was in the protocol?
The private key was being used as part of the protocol to sign certain messages.
Okay.
But in SPADE, there were no signatures.
Okay, okay.
And what's nice about the SPADE protocol is that you can do this exchange without having to have the private key. And so then your phone could get stolen and you don't really care.
Okay.
Because there are no secrets on the phone. And there's obviously your contact list is on the phone and some private information. So privacy people would care a lot, but from a security perspective, no secret information has to be lost in the SPADE protocol.
Okay.
So let me go through the file sharing and the text messaging. So actually setting up a secure file share is pretty complex these days, right? You have to collect everyone's public keys, and then you need to set this, set up you can set up an SVN or an SSH file system, but it's actually pretty cumbersome if you really have to do this in a highly secure manner. And what we've done is we built an application where you can easily exchange your public keys based on SPADE, and then automatically creates, you can just select which users you want, and it automatically creates a subset or a directory that you can mount that then allows you to perform this operation. So for example, we have here this Mobisys 2008 groups with 3 users, and all it is the keys that you've learned through this mechanism to set up this shared file system. And it was extremely easy to use. So that's the kind of applications we want to build. Things that are usually hard, but they're enabled through this exchange mechanism. Another application we've built was secure text messaging. And it's easy to spoof text messages, SMS messages sent between phones. And what we've done is we built an application that lays, it's kind of an overlay over the current SMS. So you can go to your regular SMS system, but you only see encrypted messages for the ones that have been sent with our application. Or you could go to our application, type in your password, and then it will decrypt your message. And this worked actually. You can download this, and it works on Nokia and so many phones. So we're currently working with a company who is actually building a secure SMS application for Android. And we're building a generic mechanism for exchange of public keys, essentially. So now their secure text messaging application exports their public key into our application. We then share it, and at the other end, it can be pulled out again and used then for SMS. So actually, before I mention this, let me just finish the talk, and I can give 10 conclusions and talk a little bit more about these use cases. So there have been a lot of protocols, but especially these previous ones that achieve the same group-based key exchange are all vulnerable to this group in the middle attack I presented earlier. Now, a lot of you probably know Bump, right, where you can easily exchange information. That's an iPhone, an Android application that allows you to exchange data. But actually, if you compare in Bump, you actually use a backend server. And so the problem is, in SPADE, the nice part is that your information exchange is purely local, and you're not using a server. You're also not leaking any information to the server or disclose location information. You also don't need acceleration sensors. It works with many types of phones. The security is actually very high of these protocols I presented, especially with SPADE, because attacks are detected in most cases. And also SPADE is for more than 2 users. Now Bump, the big advantage of Bump is it's really fun to use, right? You take the 2 phones, you bump it together. It's great, but you have all these other disadvantages. Now, our new system that we're building actually works on both iPhones and Android phones. And there's no communication technology that works on phones today so that they can directly communicate with each other. Like iPhones don't want to talk Bluetooth to anything but an Apple product or a headset, right? So also, unless your phone is hacked, you can't easily use Wi-Fi in a way that would be easy to share information either. So it's actually, we encountered a lot of difficulties. So we actually, for our current system, we also had to go back to using a server-based mechanism. But to our defense, we did not want to disclose any location information because that is quite private information, as well as we didn't want to use acceleration sensors because a bump itself is actually not secure. Because we want this to work among, again, iPhones, Androids, Windows 7 phones, etc. So, in summary, I believe that these physical encounters provide a really easy way for people to understand whom they set up authentic keys with. So you really want to know it's really the key from that person you've now received. And the GANGS protocol illustrated how we can use a protocol where people move around physically in order to prevent some of these attacks. And that's an interesting case. It's an interesting class of new protocols that use such human mobility for security specifically. Now, error minimization is an important aspect in which these protocols need to be improved because, again, you don't want to count in large groups. You want that if people make a mistake, that the protocol still succeeds, etc. So it's actually pretty tricky to build this protocol for large groups. Now, the current status is we believe that this is an extremely useful primitive to provide as a generic way to exchange authentic information. So we've actually hired a full-time programmer to just build the next system that hopefully you can download on Android or iPhone and then exchange information with. So our goal is to work with more companies and also other application providers. For example, this company that makes secure SMS. They use, so our system is the base system to securely exchange information. The secure SMS application exports its public key into our application, which can then be easily shared. And on the other end, this secure SMS then again extracts public keys that you've learned. And so I believe and I hope that this could be a way in which we finally achieve easy-to-use cryptography with people. And based on these physical exchanges, hopefully, who knows, this will take off, fingers crossed. But